Some time ago, we talked on this channel about FPGA-based retro systems. Take a look if you missed that video. But today it's time to talk about software emulation. It's not easy to explain in just a few words and without diving into very technical details why software emulation often doesn't feel the same as running the hardware recreated on an FPGA, even though both approaches are, in their own way, approximations of the original machine. At first I thought about making a video that would explain, in a purely conceptual way, how an emulator works. I do have some experience writing emulators. A few years ago I ported MAME, arguably the most well-known arcade emulator to Windows CE. At the time it only ran on Pocket PCs. Some of you may have actually used it. I called it Pocket Cult MAME. I also ported the excellent Amstrad CPC emulator Caprice to the same platform. And I wasn't very original with the name either. I called it Pocket Caprice. Both emulators were a real challenge because they emulated relatively powerful systems on very modest hardware. When I worked on those ports, very few Pocket PCs ran at more than 400 MHz. Many years before that, in the late 90s, I started writing an Atari ST emulator called Atari System Emulator for DOS. Only a small group of people ever had access to it, because I had to abandon the project at a very early stage due to lack of time. It seemed to me that it could be a great idea to revisit that emulator together with you, and to start programming it again, reusing some of the parts I had already written, at least on a conceptual level. I'm not going to dive into too many technical details, and I'll only briefly touch on the inner workings of the Atari ST. My goal is to explain how an emulator is built in a more general sense, rather than focusing too much on a specific system. Don't expect an emulator on the same level as modern, fully featured emulators. This is an experiment we're going to do together to discover how an emulator works on the inside, and hopefully it'll be fun. The first step in creating our emulator is to study the architecture of the system we want to emulate. The Atari ST is built around a Motorola 68000 CPU, a processor that was extremely common from the mid-80s through the early 90s, and widely used in many computers and game consoles of that era. It also relies on a Motorola 68901 MFP as its interrupt controller, a general-purpose and well-documented chip responsible for handling interrupts, timers, and input-output. Video output is handled by a custom-designed chip known as shifter. With these three core components in place, we can already begin working on our emulator. The remaining components required to get our emulator up and running, such as the memory controller, will be implemented implicitly alongside these three core elements, as we'll see later on. Other components, like the blitter, are not strictly required to boot TOS 1.0, so we'll focus first on what is truly essential, according to the service manual. To write the emulator, I've decided to use .NET Core, since C# is a mature, widely adopted language that is available on multiple platforms and offers good performance. The most important component to emulate is the CPU. It doesn't make much sense to write a Motorola emulator from scratch when there are already excellent ones available, such as Moira, a high-accuracy Motorola 68000 emulator written in C++ by Dirk Hoffmann that serves as the core of the well-regarded Amiga emulator vAmiga. The most critical part of an emulator is simulating the timing between components. This is achieved by keeping track of the CPU cycles executed by the processor we are emulating. Based on that cycle count, we can synchronize other components such as video output, audio, and the triggering of interrupts. This approach applies to virtually any emulator, but we're going to look at the Atari ST because it requires relatively few components to function, which simplifies this process significantly. In the case of a system like the Commodore Amiga, for example, things would be considerably more complex. On a PAL system, the ST's video output is composed of a total of 313 lines, each drawn at a rate of nearly 64 microseconds per line. Given that the standard Atari ST runs at a clock speed of 8 MHz, 512 CPU cycles occur during the time it takes to draw a single scan line. Putting into practice what we've seen so far, here is a simplified outline of our main loop. We will run this loop across the 313 scan lines that make up each Atari frame, and we will emulate the CPU for 512 cycles per scan line. It is important to note that the CPU does not execute exactly 512 cycles on each line, since not all Motorola instructions consume the same number of cycles. In a more accurate implementation, the execution step, or granularity, should be much smaller, and this would also require compensating for any cycle differences on the following scan line. However, here we are looking at a simplified version. In this process, we can already see some important differences compared to how an FPGA works. While in software emulation, synchronization has to be handled by software and is not fully parallel, in an FPGA-based hardware implementation, all components run independently. In our main loop, we'll generate interrupts in a synchronized way, just as the original hardware does. The glue chip sends an interrupt signal to the CPU at the end of each scan line, known as HBL, and another one when the entire frame is complete, known as VBL. These interrupts, along with hardware timers produced by the MFP, are heavily used by games to achieve effects like breaking color limits or sprite synchronization. In the Amiga, these tricks are handled by a custom chip called Copper, which runs concurrently with the CPU. That adds a lot of complexity. The ST CPU-driven approach is much simpler to implement and better for learning purposes. The next requirement to get our emulated Atari booting is memory access, specifically RAM and ROM. In the Atari ST, the MMU and glue chips act as traffic controllers. They manage the data bus and determine which component handles each request from the CPU. For our emulator, we will combine the duties of these two chips into a unified memory bus system. This module will handle all memory addressing, routing CPU read and write requests to the correct locations. In the book Gulliver's Travels, two religious factions in Lilliput are divided between those who break their boiled eggs at the small end, the Little Endians, and those who break them at the large end, the Big Endians. The Motorola 68K architecture is a Big Endian, while most modern systems today use a Little Endian architecture. What does that mean? It means that the Atari ST stores the most significant byte of any values at the lowest memory address. Basically, it stores the big part first. In practice, this means we must byte swap any 16-bit words or 32-bit double words to translate between the PC's native format and the Motorola's Big Endian architecture. Our memory read and write controller, essentially, should mimic the work of the real MMU and glue chips. It acts as a dispatcher, routing requests to RAM, a ROM, or specific peripherals, like the sound chip, the shifter video registers, or the disk controller. Diving any deeper into specific addresses would require explaining the entire architecture of the Atari ST, which is not the goal of this video. However, this example perfectly illustrates how memory access logic is handled in practically any emulator. Based on what we've covered, you should now have a clear picture of an emulator's main loop. Key to remember is that in software, components are synchronized sequentially. This stands in stark contrast to FPGA-based systems, where components run in parallel, mimicking the original hardware almost perfectly. On our software emulator, this relies on raw CPU power. If the host machine cannot process the emulation loop fast enough to keep up with the real-time clock, the simulation will fall behind, resulting in choppy audio or input lag. For this type of project, having a high number of CPU threads doesn't have a huge impact on the emulation speed itself. Since the emulated components must remain perfectly synchronized, the core logic usually has to run within a single execution thread. That said, multi-threading is still useful for handling host tasks. By keeping window management and input polling on a separate thread, the keyboard or gamepad inputs for example, we ensure the application remains responsive, simply passing those events to the main emulation loop when needed. Now all that's left is to apply everything we've seen so far to our emulator. You can download the emulator from the link I've left in the description, or clone the Git repository and explore the code to see how I've implemented all the concepts we've covered up to this point. At the time of making this video, the emulator is still in a very early stage, and there's a lot of work left to do, or at least a lot of improvements needed to make it more compatible. Even though many games and programs already run, plenty of others still have all kinds of issues. Joystick input may not respond properly, or the system may simply freeze. In many cases, this can be related to game copy protection, and loading a different cracked or unprotected version of the same game may allow it to work correctly. As I mentioned at the beginning of the video, this emulator has been more of an experiment than an attempt to build something extremely accurate, especially since there are already truly excellent emulators available of the Atari ST, and for almost any other classic computer. Still, I'll keep updating it, and I hope to bring more news about Atari System Emulator to the channel soon. Thank you so much for watching. I hope you enjoyed the video. This one was a bit more technical than usual, but I also hope you found it interesting. If you're not subscribed yet, consider subscribing to support the channel and leave a like if you enjoyed the video. See you soon.